Hi guys, what I want to do now is take some notes on examples from the textbook. So we're going to start on page 132, example 3.2. In this example, we have two people who are dragging a canoe out of a lake, and they are both pulling it with ropes. Each person applies a force of 60 newtons forward on their rope, and the force of friction exerted by the beach on the canoe is 85 newtons backwards. Start with a free body diagram, and they want us to calculate the net force on the canoe. So the way that I write my work for this is a free body diagram. You just draw a box to represent your object, so in this case a canoe, and you put a dot in the middle. Now, free body diagrams ideally have all the forces written on them. So here you can see the force of gravity that would be acting down on the canoe, and something called normal force that we'll learn later that's acting up. Now, these forces cancel out. The reason why I know they cancel is because vertically the canoe is not accelerating. So the canoe doesn't go up or down. So these forces cancel out. The net force vertically is equal to 0. They're showing you that in their analysis here. So here you can see that their vectors are drawn so that they are adding the vectors to get the net force. That's the next thing that you want to do. In the horizontal, that's where we're going to have a net force. That's where the canoe is accelerating onto the beach. So in the horizontal direction, we have a force of friction backwards, and we have two people pulling, person A and person B, with forces forwards. So net just means add up all the forces. The net force in the horizontal is going to be force person A is exerting plus force person B exerts plus force friction. The reason why I'm adding here is because these are all vectors. So what I can do is just add all my forces together and then purposefully put positive or negative signs on forces depending on what direction they're going. So here we can see net force is going to be 60 newtons that person A is exerting, same for person B, and then negative 85 newtons for the force friction because it's acting in the opposite direction. Add them all up and you get a net force of 35 newtons pulling this canoe forward. 3.3. Now we have two people pulling the canoe at an angle. So this is where we want to use our skills from Unit 1 to break these force vectors up into the components. So into an X direction and a Y direction. So the first thing I've done for 3.3 is I've drawn my force, my free body diagram. I have my canoe here, the dot. I've got my friction acting backwards, and then these 60 Newton arrows here representing each person pulling on the canoe now at a 20-degree angle. So here we can see that this angled vector will break up into force in the X and force in the Y. For me to keep this straight, I'm going to call this person A and this person B. And so this is going to be force A is exerting in the X direction or horizontally. Force they're exerting in the Y direction. Same for person B. Now I like to organize my work in columns like this. I know that I'm going to get these sides of the right angle triangle with sine and cosine. And in fact, the numbers are the same for the top triangle and the bottom triangle. They're both 20 degrees. They're both 60 newtons worth of force. So I only calculated those numbers once, and I understood that they were for both A and B going to be the same. Now, all I had to do was decide what direction or what positive or negative I was going to put on these forces. So if we're saying friction is backwards, then these forces in the X direction would be forwards or positive. There you can see your friction backwards with a negative. In the vertical, we have one of these arrows going up and one going down. So one of them is positive and one of them is negative. Ultimately, these cancel out and give you a net force of 0. This is why one of our previous questions that I assigned on how you get the maximum force is with an angle of 0. Some of the effort that these people are putting into pulling the canoe out of the water is lost because it cancels out. So essentially, they're pulling against each other and they're losing some of their force from canceling those newtons out. So all we have working for us here is the x direction. We have a net force that's equal to the sum of all of the components that we've already calculated. So here I'm adding those numbers together, being very careful to make sure that I'm adding a negative 85 because friction is in the opposite direction. Now 27.8 newtons is what you should get, and an angle of 0 degrees. So this is because in the x direction, these are all going horizontal, let's say. They're all on the same line here, so there's 0 degree difference. If one person had been pulling at an angle that was greater than the other, then of course the canoe, if you think about it, would go off on that angle. So there would be an angle if these weren't identical. Now 3.4 is a little bit of a complicated example and one that we've decided you can skip over. In this video, I'm going to explain it, however, because I know some of you are quite studious and you want to know how to do these questions. So 3.4 has a sign hanging from 2 ropes. Okay, so there's a force of tension in each of the ropes keeping the sign in place. There's some angles given here, and we can draw a free body diagram from that information. So here's my sign. Here's my force tension 1, as they have labeled it in the textbook, on an angle of 55 degrees. You'll notice that I also put in an angle of 35 here that we'll use later. Now, if I take that angled vector and I break it up into force tension vertically or in the y direction and force tension in the x direction, I can find my two components down here using my SOHCAHTOA, my trig ratios. So what you're going to notice here is that we don't actually know the number for force tension in rope 1. So what it's going to be is still just a variable in your equation. So when I calculate force tension in the y direction, it still has Ft1 in the equation. That's okay. That's going to cancel out later on. So in red and green, I have my simplified equations for Ftx and Fty that you can see here. The other thing we have happening in the x direction is there's a completely horizontal rope here, Ft2. That's another force in the x direction. There's one more force in the y direction that we have, and that's Fg, the force due to gravity that's pulling the sign down. So these two forces here must have a net force of 0 because we don't have this sign accelerating up or down. So that means that these y components cancel out. So that means we're working in the x direction here. F net in the x is going to be the sum, so add together force tension in the x and Ft2. So if I had a highlighter, I might highlight. See how these vectors are both horizontal? Those are what I'm adding up in the x direction here. Now I'm making a substitution where you see the red squiggly line. I'm putting this negative Ft1 cos 55. That's being subbed in. Now what I'm subbing in is into my y equation, f net y, I know that this is 0. So that 0 is going to help me figure out some numbers. It's the sum of gravity and Ft1y. I've subbed in mass times acceleration for force gravity, and I've subbed in the green equation from above when we did our sign ratio. Now you've got some numbers for this. You know the mass of the sign, you know acceleration due to gravity, make sure you make it a negative, and you're adding the green equation up here from your sign ratio. Now what I've done is I've done some algebra here, calculated 25 times 9.81, This was negative, so I added it to the other side and divide by sine 55. That algebra will give you a number for FT1. We now know that FT1, our original angled vector here, was 299 newtons, and this angle is what I'm going back to up here with the 35 degrees. The angle in green is my angle in standard position. So from the positive x-axis, if this was a Cartesian plane, to this point would be 90 plus 35. So that's how I got 125 degrees. Now I'm going to use this number up in my red equation because I didn't know this. I'm put in my negative 299 here, and then I can solve for FT2. Again, F net in the x direction is 0. Why? Because when we have a force net that's 0, that means the sign is not accelerating in the x direction. Since the sign is just hanging there, we know that this is true. Calculate this out and add it to the other side to get FT2 equal to 172 newtons. And if we look at where that vector is, it's pointing straight to the side. This on a Cartesian plane would be 0 degrees. Now going all the way to page 150 for one last example. So 3.6, again, we have a free body diagram here. Gravity and force normal, you can ignore those for now until we learn more. We're more concerned about the x direction, what's happening. So we have two athletes, A and B. They're in a canoe race. A has a mass of 70, B has a mass of 75 kilograms, and the canoe itself weighs 20 kilograms. Athlete A has an average force of 400 newtons forward. B is 420 forward. During the paddling, the magnitude of the water resistance on the canoe is 380 newtons. Now they've told you the magnitude, but you can imagine what the water resistance would be doing. It'd be fighting against the canoers. So it's going to be 380 newtons backwards or a negative when we plug it in. We want to calculate acceleration now. So there's one more step to do after we get our F net. So here we can see I'm calling it force friction, but this is the water resistance. Person A, person B, both exerting forces this way. You'll notice that these free body diagrams are not like Unit 1. You don't need to write things tip to tail for a free body diagram. If you were going to use these vectors to calculate the net and draw them out to scale, so with a ruler, then you would draw them tip to tail. Okay, so we're going to treat this as one system. What does that mean? That means we're not talking about this person, and the canoe separately. The box that I've drawn in my free body diagram represents all of this added up. So the total mass of this system would be 70 kilograms, 75, and 20, all added together. Here I'm saying mass total is mass of person A plus mass of B plus mass of the canoe, equaling 165 kilograms. Now we know that the vertical forces cancel out because the canoe is staying on the water, not accelerating up or down. So we're working in the horizontal direction. We're going to set up our F net equation. We're always trying to calculate the net or the sum of all forces, in this case in the horizontal direction. So that means we have a force A, a force from person B, and a force friction. Adding them all up. Now, force A was 400, B 420, and friction was 380 in the opposite direction. I would highlight this in my notes. You need to make sure that you're always adding your forces and you put a negative on the one that's acting in the opposite direction. All right, put those in your calculator and you get 440 newtons as your net force. Now, this F net is being pulled down in every part of this equation. So right here, this is F net. What is F net equal to? By Newton's second law, F net is ma, mass times acceleration. But you have to decide what mass we're using. Since we're talking about this as one system, we're using total mass. So in this equation, I would sub in mta on this side, and then you can solve for acceleration by dividing by mt. So this number here will be divided by the total mass, 165 kilograms, to give you an acceleration of 2.7 meters per second squared forward. So a vector needs direction, units, and sigdigs. That's all I have for you. If there's any questions from the textbook, please don't hesitate to ask.